All right, hello everyone. This is the review for topic 3, the first formative of topic 3. So, the first problem asks us to examine the graphs below and identify the characteristics listed. So we've got two graphs here. So we're going to look at this first graph. So it's asking me to find the domain. Domain is the possible x values that I can attain. So if I go to the left, I see that I have negative infinity. If I go all the way to the right, the graph does go off the page. But that means that graph is going to positive infinity on the right. It's very high, but it's all the way to the right. You just can't see it. So the domain, you'd write it as negative infinity to infinity. You can write it this way. Or negative infinity less than x less than infinity. Or you could be very lazy and write r for all real numbers. Okay. Next, we're asking for the range. The range is vertical. So where does this graph start to exist? It starts to exist at 3 all the way to infinity. For previous tests, I had asked you to write 3 with a bracket. This time, you're writing an open parentheses. So, parentheses 3, comma, infinity. Or y is greater than 3. The reason for this open parentheses is because there's no actual point. There's no actual point where the graph touches 3. So I'm not actually going to reach 3. This is because there is an asymptote at 3. The asymptote is y equals 3. So an asymptote means the graph gets closer and closer to y equals 3, but never actually will reach it. So if I go all the way to the end of the graph, it's going to get maybe like, so here's like 4, then 3.5, 3.2 something, 3.1, and it's going to get closer to like 3.01, 3.000, but you're never going to actually get to 3. Okay, so here's one here. All right, this graph looks very similar to the first one. So the domain is definitely the same. Negative infinity to infinity, or like this, or r for all real numbers. The domain is pretty much the same for all exponential graphs. The range is where this is a little bit difficult. So the range here, well, when does the graph start? It starts at 1 to infinity. So you see this graph's at 3, this graph is at 1. So I would write 1 comma infinity, or y is greater than 1. In this case, the asymptote also matches here, y equals 1. That is because the graph gets closer and closer to the value of 1 if I go all the way to that left side. So 1. Okay, moving along. Now comes a word problem. Let's read this. The amount of caffeine in the body typically decreases by 13% each hour. You decided to drink a single can of Red Bull, trademark, which contains 111 milligrams of caffeine. And it really does. I actually Google searched this, making this myself. So the formula for this, now this is caffeine. Caffeine does not get removed from your, it's not saying it removes 13% per hour. It continuously decreases by about a rate of 13% each hour. Since this is a continuous decrease, we're going to use the continuous exponential function, which is a equals p e to the rt. So this is your PERT equation. So we need to identify all of whatever goes in the letters. So let's think. Write an equation modeling the amount of caffeine in your system per hour. Well, what would that p be? P is how much caffeine the drink originally had. What about R? R is the rate. Well, it's decreasing, so your rate's going to be negative. Now, it's decreasing by 13%. Remember, with percents, think of them as actual cents. How would you write 13 cents as a decimal? It would be 0.13. See, 13 cents, 13%. So R equals negative 0.13. What about the time? Well, it doesn't tell me the time. It's per hour. That's actually our variable. So we'll write this as A equals P. Wait, I'm not writing the same thing again. There we go. A is 111. E to the negative 0.13 t. Remember, E is not a variable. E is that weird number, 2.72 something. It's a button in your calculator that you can press. So, here's my equation. Good, good. Next. How much caffeine will be in your system after 8 hours, round to 3 decimal places? So what we're going to do is, well, now I know my value of t. This time I want it to be 8 hours. So let's write it like this. Nope, I'm not leaving. A equals 111. E to the negative 0.13. But instead of t, I'm going to write 8. To prevent yourself from messing up, you should probably multiply things in the exponents. You can put it in the calculator just like this if you'd want. So that's 111 e to the, and now I'm going to figure out what that is. So I go to my calculator. I forgot what I was supposed to do. That's negative 0.13 times 8. That is negative 1.04. So e to the negative 1.04. Right? And then now I can just put this all into the equation. So 111, 111. Where's E? E is right above the ln button. So I press the second button so I can access e to the x. And it's going to be e to the negative 1.04. Right? What does that give me? 39.233. So 39.233. Right, I'm going to put a little squiggly equal sign to say it's about approximate. So 39.233. So how much caffeine? And that's in milligrams. So 39.233 milligrams of caffeine. Right? And now the last thing it asks is how many hours will it take until you have less than 15 milligrams of caffeine, and then round to 2 decimal places. So there's a bunch of ways you can approach this. The way that I would approach this is to just estimate and figure out some numbers. So if you want less than 15 milligrams of caffeine, that means I want to know what time am I going to get to 15 milligrams of caffeine in the body. So I write 15 equals 111 e to the negative 0.13 t. What I'm going to be doing is plugging in a few values for t and seeing if that works. So I know that if 8 hours passed, I still have 39, so it's going to be more than 8 for sure. So 111, 111, e to the negative 0.13 times, and then we're going to put that in parentheses just to be safe, parentheses, so it's longer than 8 hours. Why not 12? Is that going to be less than 15? No, that's still more than 15. So let's try this again. Second, enter. So I want it to be less than 15. So let's change 12. Let's go a little bit bigger. 15. What about in 15 hours? Oh, that's pretty close. What about 16? If I go to 16, 16, well, definitely after 15 hours. If we want to estimate it to 2 decimal places, we know it's going to be 15 point something. So it's always safe to go 15.5. So change that to 15.5. 15.5. It's definitely, well, this is less than. So we want to know when it gets about exactly to 15 milligrams. So let's see, 15.5 is 14. So let's go a little bit lower. What about 15.4? Oh, that's pretty close. 15.41. That's pretty close. 15.41. We want to get as close to 15 as possible in my answer. 15.41. And that would be 4. Let's try 0.3. So 15.3. Actually, let's try 0.39. There you go. So 15.39, I get pretty close to 15. Oh, and then after 0.39, I get 0.4. So 15.01, 15.39 or 15.40. Either of those two would work. So T is at about 15 point, let's round it to 40, 15.40 hours. So again, this is because if I put in 0.39, I get a little bit over 15, but once I go to 15.40, moving it to 40, then I finally pass that 15 mark. So 15.40 is the most appropriate, because at 15.39, I'm still a little bit above. You shouldn't have a problem that's this picky, though. So 15.40 hours. Moving to the next one here. So the world's population is growing exponentially at a rate of 1.09% per year. In 2018, the world's population is at a staggering 7.7 billion. And yeah, I did actually check this at Google, using Google. So again, this is a continuous equation again. So same thing, A equals P e to the RT. So we're going to plug in all the values. What is my P? What is R? T is just the variable in the equation. So it's going to be A equals P. That's the principal value. How much did I start with? Well, there's 7.7 billion currently, multiplied by E to the rate. The rate is currently 1.09. Since it's growing, it should be positive. You want to think about it as as actual cents. How would I write 1 cent? Well, I'd write that as 0.01 for 1 cent, and then add the 0.9 after it. So this is kind of a strange decimal. So e to the 0.0109 to the power of t. So this is your equation. And now we need to actually use our equation. According to your equation, what should the population be in 2030? Now think about it. 7.7 billion is how many people I had in 2018. Then how many years have passed? Well, 2030, it's considered 12 years later. So my t value here would be 12. 12 years later, what is my population? So let's plug in the values. A equals 7.7 e to the 0.0109, and instead of t, I put 12. So let's just find this value in the calculator. I think it's, if we're careful, we don't actually have to multiply it first. 7.7 e to the 0.0109. So there's a lot of numbers here to mess up with. 0.09, 0.109. If you put a parentheses 12, you should be safe. That is 8.776. So 8.776 billion. I'm rounding the 5 up to a 6. So that is approximately 8.776 billion people. The last question again, just like on the other page. According to your question, in what year will the population reach 9 billion? Well, the whole unit is in terms of billion people, so I'm going to set my A equal to 9. So I want to know, at what time is it going to be equal to 9? Because I know in 12 years, it's 8.7, so it's definitely more than 12 years because this is growing. So 9 equals 7.7 e to the, what is that? 0.0109 to the t. And here's where I'm just going to start testing some numbers. So complete this. So I want to know when it's equal to 9. So 7.7 e to the 0.0109 times something. Well, I know it's greater than 12. How about, I don't know, 13? How much is it in 13 years? Does it reach 9? Nope, it's still more than 13. 14? Nope, almost. No, probably 15 years. Yeah, so in 15 years, the population is bigger than 9 billion. So t is approximately 15. Now the question asks what year it is, so you need to think. 15 years after 2018, what is it? That would be 15 plus 2018. That is the year. So you'd write in the year 2033. Right, so I've answered my question here. Awesome. All right, moving down to number 4. So examine the equations below and determine which ones represent growth and which ones represent decay. I had one of those, or maybe neither, because actually one of these ends up being neither. So for growth and decay, you always take a look at what number is attached to the exponent. If the number is greater than 1, it's going to be a growth. So think about it. 2 to the power of x. This is definitely a growth because 2 is greater than 1. 0.7 to the x. 0.7 is a number less than 1, so if I keep using this number, it's going to get smaller. So this is a decay. 1/3. 1/3 is a number that's less than 1. It's a fraction less than 1. 1/3 is a decay. I got a 3, but there's a negative x. Remember, if there's a negative exponent, it actually turns it into the reciprocal. So instead of 3, it really means 1/3 to the power of x. And that is a decay. So if it's a growth and it has a negative exponent, it'll end up actually being a decay. So in reality, this is a decay. 1,000 times 1.01. 1.01 is bigger than 1. That is a growth. 0.25. 0.25 would normally be a decay, but I see that negative, which is actually going to end up changing this to a number greater than 1. I don't really want to explain this one too much, but this one is a growth. So if it's a decay, but there's a negative, then it's actually a growth. All right, this one, 0.98, it's a number smaller than 1. This is a decay. 9/7. Well, 9/7 is a fraction, but it's a fraction bigger than 1 because 9 is larger than 7. So you're going to get 1 point something. This is going to be a growth. All right, let's look here. Half. A half is less than 1, but I have a negative, so it ends up being the opposite of whatever this is. So instead of a decay, this is actually a growth. All right, what is this last one here? I got 1. Well, it's not greater than 1. It's not less than 1. So this is actually a neither. This one's neither growth nor decay, because think about it. You're just multiplying 1 over and over and over again. If you can multiply 1 infinitely many times, and it'll still be 1. Right? So next, 5. So we got 3 solving problems here. So solve the equations. Your answer should be correct to 3 places after the decimal point. So this is a lot of the guessing and trying it around. So for A, I got 4 to the x plus 3 equals 17. Well, I want to solve for the x, so first thing I would do is I'd get rid of that 3, subtract the 3. So that's 4 to the power of x. The 3's cancel, equals 17 minus 3 is 14. So I want to know what exponent is going to get me to 14. So I'm going to use the method where we just kind of keep checking it over and over and over again. So 4 to the what is 14? 4 to the, well, I know 4 squared is 16, so it's got to be less than 2. See, 4 squared is 16, so that looks like 1. 4 squared is less than 16. The 4 squared is 16, so it's got to be smaller. So 4 to the 1.5. Definitely bigger than 1.5. 1.9. 1.9 is getting close. And remember, after 1.9 is 2. So it's going to be 1.9 something. So you're going to keep trying this. 1.95. Is 1.95 good? I want it to be equal to 14. 1.95 is too big, so let's decrease it. 1.9 second, 1.92. Still bigger than 14. 1.9. Oops, 1.91. 14.12. All right, 1.90. Oh, I see. So 1.91 gets you bigger than 14. 1.90 is less than 14, so it's got to be 1.90 something. Well, this is fun. 1.905? Bigger than 14. What about 1.904? That's pretty close to 14. What about 1.903? Yeah, that's less. So I'd say 1.904 is probably the most accurate answer you can pick. So x is approximately 1.904. So it is a lot of guess and checking. It is a very boring, repetitive method, but this is acceptable right now. All right, let's take a look at B. So for B, we're actually going to try a different method. Why don't we graph these? So you could actually choose to make the equations a little bit easier before you start graphing it. You could graph it the way it is now. You could put this one in for y1, this one in for y2. So I'm going to go to here, clear what this is. So go to my graph. Remember, you press y1 for graph. So in my first, I'm going to put 5 parentheses 3 to the power of x. And I'm going to go down. For y2, I'm going to just put in y equals 40. So y1 and y2. So I want to find the intersection of these two graphs. So we're going to graph it and see. Here's my first curve, but I don't seem to see my second curve anywhere. Well, that's because your window's not high enough. See, this only goes up to 10. 40 is off the graph. So what I would do is I'd go to my window, and I want to change the maximum of the y value. So let's change that to something bigger than 40. How about 50? So the reason I want to make it bigger than 40 is so I can have a little bit of extra space at the top of my graph. Right, so it's going up there, and there we go. So this is the point of intersection, right here. So it's very hard with this calculator. I can't see what exactly it is. So this is where you use the calculate function. So press second, go to trace, calculate. And I want to find the intersection, so I'm going to move down to number 5, enter. So this one asks first curve. So you need to actually do what the graph is asking. It wants to know where's the intersection close to on the first curve. I have a little blinking cursor here, so I need to move it closer to the intersection by pressing the right button. Closer, closer. All right, that's about close enough. I'd rather be on the graph than off the graph. Enter. Now it asks for the second curve. Is the blinking close to the second curve? Yes, that's where the intersection is. Graphs will, calculators will always ask for guess. We usually are told to ignore that. Guess it, and it is. Oh, look, 1.89, and we're going to round this to 3. 1.893. So x is about 1.893. If you chose to do this the other way, you would normally divide by 5 on both sides, and then do all this. Right? And for the last one, I'm just going to show kind of like a mixture of the two methods. 2 to the exponent of x. What do? I'm dividing by 3, so I need to multiply by 3 to get it out. 3 and 3 cancel. I have 2 to the x equals 5 times 3 is 15. I need to know what exponent on 2 gives me 15. Well, I know 4 gets me 16, so it's got to be 3 point something. So again, so here's where I could test a bunch. I could do 2 to the, what's going to be 2 to the 3 point something. Let's try 3.8. No, I want it to get to 15, so 3.9. 2 to the 3.9. And that's close. 2 to the 4 is 16, so it's between 9 and, it's between 0.9 and 4. So I'm just going to keep doing this over and over again. It is really boring. So you could do it that way, or you could actually put both of them in the equation. Well, I've already done it, so I can actually do 2 to the x in one equation and 16 in the other. 2 to the power of x and then 16 in the other one. So you don't actually have to put, oh, not 16, 15. So you don't actually have to put the original equations into the calculator. You can put one that's a little easier after you've done some solving. So it's okay that I didn't put the original in. Let's graph it. Okay, let's find the intersection. There we go. It's like 3 point something. Second, calculate. Go find the intersection. Move the cursor by pressing the right button. Move it close to the point of intersection. That's about close enough. Is this on the second curve near the intersection? It absolutely is. And ignore the guessing. And yeah, 3.9 something. So I could have estimated it or done it the calculator way, 3.907. So x is approximately 3.907. So you can choose whichever method you want. Either way is fine. Right, next. Okay, write the exponential equation that would match each pair of points. So the exponential equation that we want it to look like is y equals a times b to the x. So remember we learned that if you have a 0 as an x value, you're going to get b to the 0, which just cancels out. So I'm left with y equals a. So the y value of 5 really is the a value. A equals 5 because I have an x value of 0. So now that I have a equals 5, let's put this point into the equation as well. So y equals, well, y is 40. So 40 equals ab to the power of 3. Well, I know that a is 5, so I'm going to use a equals 5 in this equation. So I'm going to put 40 equals a, which is 5, b to the power of 3. So I'm trying to solve for what the b is. Remember, you can't get rid of that exponent unless you deal with that 5 first. I need to divide both sides by 5. The 5's cancel up. 40 divided by 5 is 8. B to the power of 3, bring that down. And then, let's see, I'm trying to solve for b, so I need to take, how do I get rid of that 3? You need to apply the cube root on both sides. So, changing colors. I'm going to put the cube root on both sides. Cube root of 8. Cube root of 8. What is the cube root of 8? The cube root of 8 is 2. So, b equals 2. Cool. I have my a, I have my b. Let's all put this into the equation. So my equation is finally y equals 5 times 2 to the power of x. So this is my first equation. All right, now let's do the same thing for the second equation. This one's a little bit more difficult because I no longer have an x value of 0. So I need to put both of these into the equation. So y is 8. 8 equals ab to the 1. But remember, if I have an exponent of 1, I don't need to write anything. Next, let's follow this equation again. What is my y value here? 128 equals ab to the power of x, which is 3. Great, I have two equations. The method we learned was to divide one equation with the other. Take the larger equation, divide it by the smaller equation. So this is going to be, let's see here, 128 equals ab to the power of 3. And I'm going to divide 128 by 8, ab cubed by ab. 128 divided by 8, that is 16. The a's will cross out. I have b to the power of 3 and 1b here. I have 3 b's, 1b divided. That leaves only 2. Well, all right, b squared equals 16. What number multiplies to get 16? I could use negative 4, but that's not going to help me here. So positive 4. So b would equal 4. That's because 4 times 4 is 16. Well, I have my b value. I still need to find my a value. Why don't I use the first equation? You could actually choose any equation, but please, you want to use the one that's easier. So let's use b equals 4 with the first equation. So 8 equals a times, and instead of b, we're going to put 4. So I have a times 4. How do I get rid of this 4? Divide both sides by 4. These cross out. 8 divided by 4 is 2. So a equals 2. I have my a value, I have my b value, and we're finally going to put it all in an equation. Y equals 2 times 4 to the power of x. So here's how you have the equation if the x value for one of the points is 0, and this is where you have none of the x values being 0. All right, moving to the last one, you have recently inherited $10,000, lucky you, and plan to deposit into a savings account for 10 years. You have 3 options to choose from. You got Bank A, Bank B, Bank C. And you want to know which bank gives you the most money after 10 years. So this bank each of the banks talk about compounding. Compounding monthly, compounding daily, and compounding continuously. If I'm compounding monthly, we refer to this as our n value. N is 12 because I compound 12 times in a year. If it's compounding daily, n is 365. Compounding continuously, when you see that word continuously, that means I have to use e. N is not equal to e. It just means you need to use e in this equation. So the compound interest formula is, let's write it over here. That would be A equals, parentheses, 1 plus r over n to the power of n t. You don't need to memorize this formula. All the formulas should be provided for you. So what we're going to do is we're going to plug in these numbers for Bank A, plug it in for Bank B, and for Bank C, I need to use A equals P E R to the T. If it's compounded by any number, if it's compounded by regularly, we use this formula. If it's compounded continuously, we use that. So let's just apply the formula to everything. So for Bank A equals, actually on the formula I forgot to put one thing. That should be P. You need to include your principal. So let's rewrite this. A equals P times 1 plus R over N to the NT. Apologies for that. So what is my principal? How much do I start with? Oh, well, I inherited $10,000. So put in 10,000. Usually you don't really put commas in formulas, so we're going to just remember how many zeros that is. 1 plus R, the rate is 2%. 2% as a cent would be 0.02. This is how you write, like 0.2 cents. Divided by 12 to the 12, which is your n value, times t. Well, it asks for 10 years. Oh, 10. So what we're going to do is we're going to find the value for this, find the value for the second one, find the value for the third one, and compare all three. So let's write all the formulas first. And why don't we do one in a different color, just to not get confused. So what's this one? A equals 10,000 times 1 plus 0.02 over 365 to the 365 times 10. And for the last one, this is the easiest equation to use. A equals 10,000. Probably should have given you a smaller number. E to the RT. The rate is 0.2, so 0.02 times t, which is 10 years. So you need to know how to use these formulas. You're not expected to memorize them. So this is where the wonderful calculator comes in. All right, let's erase this graph when you're done with this. Let's second quit out of that graph. So, all right, so 10,000. 4 zeros, good. Parentheses, 1 plus 0.02 divided by 12. And the exponent I'm going to be putting is 12 parentheses 10. How much money is that? That's $12,211.99. So 1, 2, 2. There we go. So this is how much money you're getting from the first bank. We're going to do the same thing with the second bank. So the formula is, well, it's the same thing. I'm just writing 365 instead of the 12. So I'm going to use second. Actually, this might be a little bit more difficult. So let's erase it and just start from the beginning. 10,000 parentheses 1 plus 0.02. And remember, for fraction, you're just using the division symbol. Divided by 365 to the power of 365 times 10. And that is $12,213.96. A little bit more. So compounding daily is a little bit better. So this is approximately 12,213.96. Last one. This is the easiest equation just because all you need to do is just put E. All right. So let's erase this. This is giving me a headache. 10,000. All right, 10,000. E. There we go. E to the 0.02 times the time, which is 10. Nope, messed up. 10. Oh, all right, 14. So I earned a little bit more. Not really that much more, though. So that is approximately equal to about 12,214.03. So the third bank definitely gave me the most money here. So you would write finally, which one gives you the most money? Bank C gives the most money. Ooh, my handwriting is terrible. Bank C gives the most money after 10 years. And if you're asking for the explanation, if you just wrote this, this is considered enough of an explanation. One thing we noticed, remember, if we're comparing banks with the same % interest rate, compounding continuously is always the best. The more you compound, the more money you make. So this is always the case here. So these are all the questions, and that's it.